going to be learning two other techniques that will help us with integration. We are skipping 7.3. If you notice on the syllabus, we skip 7.3, jump to 7.4. 7.3 is entitled Tables of Integrals, which if you're not aware, if you have your hardback book, in the back of the book, there is a bunch of integration tables. Like, it gives you the integral of a bunch of different functions. Well, guess what? On the AP test, you're not going to be able to use any of that, so why would we spend time using integration tables? We need to be able to use the techniques that we're learning to be able to integrate particular functions. So what we're going to be doing in 7.4 is using two different techniques. One of them is called partial fractions, or some people call this partial fraction decomposition. And then the other one we're going to be using is called trig substitution. So we're going to be using some substitution with trigonometry to be able to do those, but we'll get to that here in a minute. So with partial fractions or partial fraction decomposition, what we want to do is take an integral that is maybe like this: 1 over x squared minus 7x plus 10 dx, and be able to integrate that. Now, if we go through the list of things that we've learned so far, this is not one that we just know. This is not one we can undo the power rule, because if I kind of write this, I could write it as x squared minus 7x plus 10, all of that raised to the -1, but that's not really helping me. You might think substitution with this problem and just pick the entire denominator, but if I picked the entire denominator on this problem and called that w, dw would have all sorts of x's in it still, okay? And we don't have any of that other stuff in this integral, so that is probably not a good technique, and also probably not a good idea to solve for dx like we did on one of the homework problems before, because then I'd have to be able to know what x is, and I can't really do that nicely. I could do it, but I can't do it nicely. So we're down to something called partial fractions. And in the idea of partial fractions, what we want to be able to do is to break up this fraction into two fractions, or what some people like to call this is decomposing a fraction. So a lot of times we talk about putting two fractions together using a common denominator. What we're going to do in this lesson is break the fraction apart and kind of undo the idea of getting a common denominator. So first of all, how in the world could I look at this? Well, I would probably, with a denominator like this, try to factor. What does this denominator factor into? What are the two terms there? Yeah, Naya? X minus 5, x minus 2. So definitely we have two factors in the denominator that are there, and we can create that, and that will allow us to see that really what I have here is an integral of something, which I'm going to call a, over an x minus 5, plus something over an x minus 2. I'm breaking apart that fraction into two fractions with different denominators. And what we're accustomed to doing is taking something like I wrote here and getting a common denominator to get that. So now we're breaking this apart. So the way that I can find the a and b that make this work is to go through the process of getting a common denominator. Because what I know is that this numerator has to be 1, but the numerator here is created by getting a common denominator. So we know that 1 is going to be equal to something in terms of a's and b's. So think to yourself, what would I do to get a common denominator over here in this integral that I wrote at the end? Well, what would I do to this first fraction to get a common denominator? So multiply by x minus 2. Just x minus 2 here. On the bottom as well. X minus 2 times x minus, or sorry, over x minus 2. And then for the other fraction, we're multiplying by, to get a common denominator, x minus 5 over x minus 5. And why can I do that? I can do that because what I wrote in blue is 1, and what I wrote in red is also 1. Multiplying by 1 does not change the meaning of anything. But what it does is it allows me to see that this 1, which is in the numerator of my original integral, has to equal a times x minus 2 plus b times x minus 5. The numerator of this integral in the middle has to be equal to the numerator of the integral at the end. And hopefully you can see that we're going to be able to find the a and the b that make this work. Now, you might be using a little bit of algebraic technique that you're not accustomed to, but I think it'll make some sense to you. I would distribute this out, and this would give you ax minus 2a plus bx minus 5b. And I would even go further and combine my a's, my x's, and then my constants. So I know 1 is equal to, I have ax and bx. So one way that I could write that is a plus b times x. And that's the way I'm going to choose to write that. Now, if that's too much of a jump for you, then maybe this next step would be important, where I just say ax plus bx minus 2a minus 5b. And then, not quite done with my red step here, I would have plus a negative 2a minus 5b. So what I have here is coefficient of x, and I have a constant. And if this is a true equation, what has to be true about the coefficient of x on the right side of the equation and the coefficient of the x on the left side of the equation? They're the same. Now, over here on the left, how many x's do we have? We don't have any. There's 0 x's. So what that means is this coefficient of x has to equal that coefficient of x. So we now know that a plus b equals 0. By the way, we also would know that 1 has to be the same thing as what? This constant over here. So we could say negative 2a minus 5b equals 1. And we get a system of equations that we can solve. We get 2 equations with 2 variables, and we can solve this. And you might be thinking to yourself, man, that is a lot of algebra. Yep, yes it is. Okay, which is why you do all this algebra coming up to this class to be able to do things like this that are a little bit more complex. So what do we know? From this first equation, we know a is equal to negative b. And then I could make a substitution over here in the green equation. For a, I can put negative b. What that's going to give me is 2a. Negative times negative is positive. Or sorry, 2b, not 2a. 2b minus 5b is 1. So what does that mean b is equal to? I combine my terms, divide. Negative 1/3. We got a number. Okay, so what's a equal to? If a is the opposite of b, that's b 1/3. All of that work was kind of a little bit of a side note to be able to determine what this integral really is. So now I have an integral where I've got the integral of 1/3 over x minus 5 plus negative 1/3 over x minus 2 dx. Those aren't really nice coefficients, but the good thing for us is I could just pull that coefficient out front, and I could say that this is 1/3 times an integral of 1 over x minus 5 minus 1 over x minus 2 dx. And you might not realize it, but those are actually two integrals that we could do. Those are actually integrals that we know. So this is 1/3. What's this first integral going to be?
Negative 1.
Nope. Anyone at home want to chime in for what this first integral is? And I have a 1 over something to the first power. That's an ln. So that's the ln of the absolute value of x minus 5. And I really don't have to worry about substitution because the derivative of that denominator is just 1. And then I'll have minus the ln absolute value of x minus 2 plus a constant. When we use this technique of partial fractions, we get a lot of natural logs. Not always, but we get natural log quite often. This, if it was a multiple choice question, probably would look a little different. We could use a property of logarithms that allow us to take this ln and subtraction of ln's and combine as division. So absolute value of x minus 5 over x minus 2. And if you really wanted to, you can put that 1/3 as an exponent. A lot of times it just stay out front. But that is the antiderivative of this thing way up at the beginning when we started it. Complicated technique, yes. A lot of algebra, yes. But something that allows us to take an integral that we are not able to do and turn it into one that we can do. Questions on this technique as we move forward? All right. I would like for you to try this one on your own, and then we'll talk. The integral of x plus 2 over x squared plus x dx. And you might think to yourself, oh, I can do a substitution really nicely, but the derivative of the denominator is 2x plus 1, not x plus 2, and it would be hard to make that substitution. So partial fractions is the way to go. Give it a try. Those of you at home, give it a try too. All right, let's see what we got for this. First of all, how does this factor in the denominator? We have an x times x plus 1. Numerator is x plus 2. And so therefore, we want to split this into an integral of something over x plus something over x plus 1. So my somethings are going to be an a and a b. So to go through this process of getting a common denominator, you're going to take the a and multiply it by x plus 1. You're going to take the b and multiply it by x to get the numerator. And that numerator has to equal the numerator in the previous step in green, which is x plus 2. Doing some simplification here, we can distribute through and get ax plus a plus bx equals x plus 2. Which means if I jump to the step where I've got my factored coefficient of x, we have an a plus b times x. We have an a, which has to equal x plus 2. That leads us to a situation where we know two things. A plus b equals the coefficient over here, which is 1. We also know the constant has to equal the constant, so we also know a is 2 directly. We know that. So if a is 2, 2 plus 1 equals 1, negative 1. B is negative 1. So now my integral becomes the integral of 2 over x minus 1 over x plus 1 dx. And again, the idea is to get an integral that we can actually do. And this is one that we can actually do. So antiderivative of 2 over x is 2 ln absolute value of x. Antiderivative of 1 over x plus 1 is minus ln absolute value of x plus 1 plus a constant. Again, we could use properties of exponents here, or not properties of exponents, properties of logarithms. But before you do that, what you'd have to do is put the 2 as an exponent. Why I said exponents. And technically what that squared would do is make sure that you wouldn't have to actually use the absolute value there. Because if that's squared, it's always going to be positive. So that would technically mean you'd have the ln of x squared on top, the absolute value of x plus 1 on the bottom. Now, is it okay in your homework to leave it like this? For sure. But understand that if you were doing a multiple choice part of the test, you would have to be able to simplify down to one of the solutions by using some of those properties of logarithms. If you can get to this part here that I put a star next to, I'd be super happy. Okay, so get there. A couple other kind of nuances with partial fractions. They don't show up a lot, but there are a couple of problems in your homework that deal with something like this. If you have a situation where we have an integral like 10x minus 2x squared over x minus 1 squared times x minus, or sorry, plus 3, like that. What do you notice that's different in this problem? We could factor the top. The bottom's already factored. What I want to focus on is how that bottom factored. What do you notice about the factors in the bottom? There's a squared factor, which means that's a repeated factor. When you have a repeated factor, you need to do something in terms of your decomposition. And the reason why is because what if I had something like, I don't know, what if I had 1/2 plus 1/4 plus 1/3, and I wanted to combine all those fractions together? What's the common denominator of that? 12, right? That's 12. So that 12 means that this really is 6/12 plus 3/12 plus 4/12. And what that's going to end up with is 13/12. If I asked you to decompose this 12 here, this denominator of 12, you wouldn't know what factors you possibly could have. You might have a 2, you might have a 4, you might have even a 6 instead of the 3. We're not sure there. Some of those factors are repeated. They're multiplied, like this 4 is 2 squared. So how do I know how many of these there actually are? So the kind of trick, and we're not going to finish this problem, but the trick that you would use when I have a repeated factor is that you would need to include each of the factors that are possible for the denominator. So we definitely have an x plus 3, so I could say a over x plus 3. We definitely have, or could have, an x minus 1 squared, so I could say b over x minus 1 squared. But kind of like over here I had a 4 and a 2 as a denominator, I could also have just that to the first power, that x minus 1 to the first power. So that means I would have 3 fractions that are possible for this decomposition. Might it be that one of these coefficients, a, b, or c, is 0? Sure. And then I wouldn't have one of those, but I have to account for a possibility of having all of those. Like if I had 12ths, how do I know that my 12ths aren't a combination of 6ths, 1/3s, 4ths, and halves? I don't know that. It could be 4 fractions added together. I have to account for all of those, and that makes it a little bit more complicated. The other little nuance that could pop up in these partial fractions is the possibility of having a non-factorable denominator term. Or I probably should have said non-factorable term in the denominator. But what I mean by that is if I have a 2x squared minus x minus 1 over x squared plus 1 times x minus 2. If I kind of think of the idea of division, and we don't do a whole lot of long division in this course. We don't do any actually, but there are some calculus courses that do some integration by long division. If I were to split this into an x squared plus 1 as a factor and then x minus 2 as a factor, I can't factor this x squared plus 1 anymore. That's as far as it factors. But if I were to kind of divide these out, there's a possibility that since this denominator is a squared term, there's a second degree term in there, to get a proper fraction, I could possibly have a linear term left over on top. So you would have to account for a line, ax plus b, and then you would have over here just a c. So again, if I think of this as a proper fraction, that would mean the degree of the denominator has to be bigger than the degree of the numerator. Well, that means on the second term, I've got linear in the denominator, so that has to be, sorry. So I've got linear in the denominator, that has to be a constant, one less than that degree. If I've got a coefficient, or not coefficient, if I've got a quadratic in this first one, I can have a line in the numerator. That does not show up very often, but it does show up occasionally. Can you remember if that's in the homework? I know the first one where I have a repeated root is in the homework. So make sure you're aware of that.